Hello, everyone. I'm Zeke. So, when I was 8 years old, I wanted to know how to contact an astronaut on the International Space Station. And as it turns out, they have a ham radio up there. So I got my ham radio license and started building my own homemade antennas and satellite tracking systems to be able to contact it. So this is a Lego prototype satellite tracker that I made, and I used it to test my code before putting it onto my full-size satellite tracker here. And these two trackers use potentiometers for position sensing, and I used this big one on the right to be able to contact the ISS repeater. So the way this works is I send my signal up to the ISS, and it retransmits it back down to other people on the ground. So each one of these pins represents a different person who I've talked to through the ISS repeater. So because I'm based here in Portland, the farthest people who have talked to is someone in Nashville and another guy in Alaska. But the problem was I wanted to talk to an astronaut, and astronauts can't just sit around waiting on the radio to answer calls because they have other things to do. So I needed a way to schedule a call with an astronaut. And that's where AIRS came in, Amateur Radio on the International Space Station. And they are NASA's educational outreach program who schedule calls between students and astronauts. So I submitted a proposal to use my homemade equipment to be able to contact an astronaut. In December of 2023, I heard about the Oregon State Science Fair, NWSC, and because I only heard about it in December, that meant that I only had 3 months to complete my project, a 3D printed desktop satellite tracker. Now, why 3D printed? Well, that's because all of my other desktop-sized satellite trackers were made out of Legos, so I wanted to try something new. But the problem was I didn't have a 3D printer, and I didn't know how to use one. However, I was able to make this 3D design of it. Now, the desktop satellite tracker uses a planetary gear system here, which is in 2 stages. So it uses the motor drives this drive gear down here, which drives the planetary gears here, which connect to this ring gear on the bottom. And then that drives the second stage here, which slows down the speed of the motor from 400 RPMs down to a more manageable 17. When I did get my 3D printer, it had quite a steep learning curve. So each one of these prints is an attempt I made at the tracker before it actually worked. And there's probably at least 80 prints in this picture, and there's more than that. Now, remember the potentiometers from this first slide? They're okay, but they have a big problem, and that's because they do not rotate forever. So to fix this, I'm replacing them with a magnetometer and an accelerometer. Now, what are these? Well, a magnetometer is basically like a compass, and no matter how many times you rotate a compass, it doesn't twist up. You can rotate it as many times as you want. And the accelerometer just measures the acceleration, so it's really just telling me where down is. So great, now I can replace my potentiometers and be able to rotate forever. Now, notice the scale of these components here. That's 1 millimeter. And you might think that these are very hard to solder on by hand, which is what I was doing. But they're actually some of the easiest components to solder because they have little balls of solder on each of their pads. So all I have to do is add a little bit of flux paste onto the pad, place the component on, and heat it up, and then it will solder itself and snap into place because of the surface tension of the solder. So now we get to more of the circuitry of the desktop satellite tracker, and this is the baseboard. Now you can see there's quite a few things on it, so let's go through them one at a time. We have our ESP32 here, which calculates the position of the satellite, and it also tells the motors where to point at it and how fast to go and all that. The LCD screen here displays satellite telemetry, and I can control it with these buttons to select a satellite to track or a planet or a star. I also have a GPS module here, and I need this because the 2-line elements that I get for the position of the satellite only give me XYZ coordinates from the center of the Earth given a time. So I need my position on the ground to be able to calculate where to point my antenna as a look angle from where I am. I also have my serial here to be able to talk to it and tell it what to track from the command line. Finally, there are these 3 prongs here, and on the bottom of them, I have these battery contacts. Now, why are these for? Well, the battery contacts have 4 connectors on each of them, and they press onto the 4 rings of the circle board. Now, the whole point of the magnetometer was to make it so that I could rotate as many times as I want. But there's still electronic components which need power, and wires that would normally be used to transfer that power would twist up if I used them. So the circle board acts as a slip ring so that I can get power to it no matter what orientation it's in. And that allows it to get power. So the flex board that holds the magnetometer and accelerometer, it's a flexible PCB, goes into a flexible PCB connector, which connects right here. And this is for the desktop satellite tracker. And this is the flex board, so you can see the magnetometer and accelerometer there. And there are a few problems that I had when I was making this. One of those problems was that my traces would constantly crack at the edge of pads like this. So I would have my trace and then a hard junction before my pad. And that would just break off. And this is due to a few reasons. One of those reasons is the weight of the motors pulling on it. Because it's a flexible PCB, it's actually bending. You'll see that in the next slide. And the hard junction. And it's actually meant to bend at all of these places like this. And you can see there's one there. Well, actually, that's the motor, but never mind. Anyway, to fix this problem, all I have to do is get rid of the hard junction by adding what's called a teardrop, so that gradually increases the size of the trace into the pad. And then they don't break anymore. And you can see how it bends there. So now I want to talk about some more of the problems and solutions that I had for it. So some of the problems I had were my motors, their pads would actually tear out of the board when I would solder them on, and the surface mount components would have the cover lay actually melt over their pads. So to fix the pads tearing out of the board, you can see originally there's nothing keeping this small pad from just coming out of the board except for these 2 tiny traces. So to fix this, I increased the size of the copper to be this big now, so I don't have that problem anymore. And for the melting cover lay, I was using way too much heat, so I just need to use less than 250 degrees C for the surface mount components, and no more than 300 degrees C for less than 5 seconds when I'm soldering the through-hole components like the motors. So I know that my potentiometers were fairly accurate, but I want to test the accuracy of my magnetometer and accelerometer. So I tested the accuracy of the magnetometer here with another magnetometer, a phone compass. And I found that the greatest error it had was when it was pointed east with -7 degrees. And that's acceptable. So now I want to test the accuracy of my accelerometer here. So the first thing I did is I leveled it with a level. And then I rotated it up to where it measured 90 degrees, and I calculated that its error was 14.2 degrees. Now, that's quite a bit. It's more than double what the magnetometer's error was. But what I can do is manually rotate it up to where 90 degrees actually is, and then interpolate between where 90 degrees and 0 is, and that will give me very accurate positioning. So I don't need to worry about this error anymore. At the science fair, the desktop satellite tracker won quite a few awards. So it got first place in the engineering category and best of fair in middle school. And it also got second place in the math category at the National Science Fair. And by the way, the ARIS proposal was accepted, which means that I have to start working on the technology to make the ARIS contact possible. And that's where this full-size satellite tracker comes in. It's right here, right here. And it uses the same circuit boards, so it uses the same baseboard and circle board. And it also uses a magnetometer and accelerometer. So basically everything's the same. Really the only difference is the outside. So I made it more robust, and I also made it waterproof. You can see all the contours on this lid for it to keep all the water out. And that's because I was going to use it outside in the weather. And because it's Oregon, it has to be waterproof. And also, instead of having a planetary gear system to connect it, I'm directly connecting it. And that's because these motors are very slow already. They're internally geared down to 0.5 RPM, so I don't have to gear them down externally. So this is a direct comparison between the full-size satellite tracker and the desktop satellite tracker. And you can notice that the desktop satellite tracker's antenna is right there, but there doesn't seem to be one on the full-size satellite tracker. Where is it? Well, there's actually a 10-foot long 2x2 post that goes through the center here with a 2-meter antenna on either side, and you'll see that in a few slides. Now, you can see the circuit boards here, but where are they on the full-size satellite tracker? Well, if we open up this section, we can see that they are, in fact, in there, and that's what it looks like. So then I led a workshop to teach students from my school how to build the 2-meter cross-Yagi antennas that would be used for the contact. So I taught them to build circularly polarized cross-Yagi antennas because I need to be able to contact the ISS no matter what orientation it's in. And circular polarization allows me to do that. And that's what they look like. So you can see how the antenna is attached to the full-size satellite tracker in the middle. And so now I'm going out to the location where the contact would take place at the Carleton Observatory, at the Evergreen Air and Space Museum in McMinnville. And I'm testing my setup. And as I'm doing this, even 10 days before the contact, I wasn't sure if it would work because I had an immunity problem where the transmitting RF from the antennas would interfere with the weak I2C signals of the sensors. So I had my grandma sew a 10-layer RF shield out of RF fabric to completely encase the satellite tracker. And this is what it looked like. And this would go over it with the post going through it. And that fixed the problem, mostly. And finally, on October 18th, 2024, it was finally time to attempt to contact the ISS. So many things had to go right for this to happen. I only had one shot while the ISS was passing overhead for only 10 minutes at almost 18,000 miles per hour, which means that there is no time for troubleshooting. At 7:30 a.m., there is an empty field, and everything has to be set up from the ground up before the ISS passes over the horizon in just a few hours at 11:28 a.m. There are 100 people on site and 400 people on the live stream, along with live TV crew who are filming the event. The clock on the satellite tracker has to be synchronized to the second, because if we're off by even 10 minutes, we'll completely miss the ISS pass, because the two line elements that give me XYZ positioning for the satellite from the center of the Earth need the time to be able to calculate that position. The GPS coordinates also have to be correct, so I can know my look angle to it. And the TLEs have to be up to date, because if they're wrong, I'll just point in the wrong direction. The RF shield has to eliminate the interference, because even though it usually worked, it was not 100%. The magnetometer and accelerometer needed to have correct data, or they'd point in the wrong direction. Specifically, the magnetometer couldn't have any magnetic interference. Otherwise, it would point in the wrong direction. The low noise amplifier had to not only amplify the signal from the ISS, but it also had to shut off while I was transmitting so I didn't fry it, which happened a couple times. The Doppler shift had to be manually tuned because if I drifted too far away from the signal of the ISS as it was passing overhead, it would start to get weak. And there couldn't be any feedback from the soundboard because if there were, we wouldn't be able to hear anything. Finally, the signal also had to get around a nearby building. And as the ISS pass was happening, we realized that the ISS would be passing from directly behind that building. So 1 minute after the ISS passes over the horizon, it's 11:29, and all we're hearing is static. There is no ISS signal. At 2 minutes after the ISS passes over the horizon, there is still just static. There's no signal. Is it working?
Anyone assess? Anyone assess? Anyone assess? This is Kilo Juliet 7 November Lima Lima. Kilo Juliet 7 November Lima Lima. November Alpha 1 SS over. Sunita, this is Kilo Juliet 7 November Lima Lima. It is a great honor to connect with you today. I read you 5.
So it did work, and all of the students who were asking questions were able to get all of their 20 questions in during the 10 minutes of the contact. Actually, 8 minutes of the contact because we missed the first 2. Also, this was the very first homemade ISS contact to use completely homemade equipment, and what I mean by that is homemade satellite trackers and antennas, since it started in 1996. Also, this was the very first time a magnetometer and accelerometer had ever been used in a satellite tracker. So if you have any questions, now would be a great time to ask them. Actually, you keep this. Okay. Yes?
Did you exchange QSL cards with the astronaut you spoke to?
So I did get an Eris ISS QSL card from the ISS. However, it was not the astronaut's QSL card. It was the Eris's ISS QSL card. Huh? Yeah.
Awesome talk. This is so cool. Can you do this with a regular technician ham license, or do you have to have some kind of specialized license to talk to the ISS?
Yeah, so I use the 2-meter band, so whatever license does that, it is the technician license, so you only need a technician license to be able to talk to the ISS.
Thank you.
Saw someone else here?
You seem to be begging for this question since you mentioned magnetometer and accelerometer hadn't been used previously, and I was curious, how are you keeping those calibrated, particularly the magnetometer?
Okay, so I spin it in a circle, and then I take the maximum value and the minimum value that the magnetometer records, and I use that as my calibration for where to calibrate it where it is in its current magnetic field, and then it gives me positions. Yeah?
Did you record what the terrain elevation angle was when you first made contact and what the antenna elevation was?
Oh, okay, that's a good question. So on the live stream, were we recording it? Were we using the record function of the terminal when we? No? Okay. So it might be on the live stream. I don't remember if I was showing the terminal, but oh yeah, I think gpredict shows it, and that was on the live stream. So I think you can. There is a way to figure out what the elevation angle was when I actually made contact. Yeah.
natural follow-up to that question. Did you make link margin predictions, and do you know how close the actual link margin was when you made contact?
Well, basically just point at the ISS and hope that your signal gets there. That's really all I could do. But have good SWR on my antennas, and then point at the ISS, and then that was my job. I didn't have any predictions for when I would actually get the signal. Yeah.
So it looks like maybe your YouTube channel is the same as your call sign. Is that the best place for people to follow your projects, including this one?
Yeah, that is the best place. My QRZ page is wildly outdated, so definitely go
Classic.
to the YouTube channel. Yeah, you in the back.
Apologies if I missed it. Did you mention the transmit power of your transceiver?
Oh, okay. So its maximum was 100 watts, and that's what Iris wants you to be capable of. And so my antennas were blasting out 100 watts, and the side lobes, the radiated power, part of it was going into the I2C communication, and so that would break things. And so we needed 10 layers of this RF shielding fabric to be able to stop it from interfering.
On your YouTube channel, is there the 20 student questions?
Yes, so you can go to the live stream or the shortened live stream and then watch the whole entire 8-minute contact.
All right. Give it up for Zeke. Thanks.
Do we have time for one more question?
Sure, one more question.
This is super cool. I guess my question is, what's next?
Well, if you've ever worked on a project for almost half your life, you'll know that after it, you need a little bit of a break. But I have had plans to make a octocopter that goes up 400 feet into the air with a 2-meter phased array antenna on it. And that could act as a directional repeater. And it can only go up 400 feet. Otherwise, I'd have to register it as a tower with the FAA. And I also have a plan to, an idea to make a hexcopter that can transport 4 people to anywhere and land in a parking spot.